Guys, in today's lecture we are going to cover the heat gain and heat loss, and slightly we are going to talk about the load calculations for heat gain and heat loss. And at the end of today's lecture you should be good with the infiltration, ventilation, impact of occupants on ventilation, and also the lighting effect on ventilation, how the ventilation is affected by the lighting inside the house or inside the any type of building. Efficiency and the outdoor air, heating and cooling loads, and also the slightly again in today's lecture we are going to cover the load calculations. Before going to make an explanation about the differences between infiltration and ventilation, I have just a few questions that can make it better for us to understand why infiltration and the ventilation are important in this topic. So I have a question here: how is building air quality maintained? So the building's air quality is maintained by introducing a continuous supply of fresh outdoor air. So outdoor air is fresh, so inside the buildings we are using the air, so it is not that high quality air, so we have to replace some of them with the fresh outdoor air so that the building air quality will be maintained. And another question is, fresh air supply reduction saves heating and cooling dollars. Definitely this is correct, because if we keep the same air inside a building, inside a space that is already conditioned in a sense that heated or cooled, so there's already good air inside it in terms of the temperature wise that we need. However, the quality of it is not going to be as good as the fresh air. That's why fresh air supply reduction saves the heating and cooling dollars. However, what may be the danger in adopting this measure? Okay, if we adopt this, which means that reducing the fresh air supply, okay, it may cause health problems because of the quality of the air again inside the building, even though it is conditioned air, heated or cooled air, but it is not a fresh air anymore. It is used a lot of times, so that's why it may cause health problems and encourage the sick building lawsuits. In the past there were some lawsuits related with this sick building issue, and that's why we have to provide enough fresh air, even though we know that we are not gonna save so much of the money, but health is the utmost important thing for us, so we have to pay more attention on that one. So how much fresh air do we have to supply? This is the question now. So we are saying that actually not us, but the authorities are saying that 15 CFM is cubic feet per minute. Okay, each minute 15 cubic feet volume of a fresh air or more per person is recommended for most building occupancies. Okay, so per person we have to provide at least 15 cubic feet per minute fresh air to the space so that the air quality will be maintained. And this number changes, and especially I have some information from the old years. There were hotels. In hotels this number goes all the way to 30 for bedrooms plus 35 CFM for bathrooms. Okay, 30 for the bedrooms and 35 for the bathrooms in the hotels. And if you're going to places, it's not very common in the States, but there are still places in Europe that smoking is allowed. So in those places the fresh air intake share is around like 40 to 50 CFM, and depending on the location, on the number of the people, this number is subject to change. However, again, this is minimum required CFM per person to provide enough quality air. And here, most homes, like the residential constructions, rely on natural infiltration for fresh air, because we have like the cracks or the openings under doors near windows, and some heat losses when you guys open the doors and stuff. So that's why most homes rely on the natural infiltration, so no need for the ventilation most of the time. However, in a sealed tight commercial buildings, ventilation is important to provide the fresh air. So infiltration and ventilation are two ways that the fresh air is maintained, or fresh air is supplied into the living spaces, okay, to the buildings. And commercial buildings, since they are really sealed tight to prevent the loss of air, they gotta be ventilated. And the residential buildings, the homes that we live in them, and they rely on the natural infiltration. So infiltration occurs, we cannot prevent it through the openings under the doors, next to windows, and when we open just the doors, or again some cracks and in, I don't know, maybe in the side of the walls or something. So these are gonna provide the natural infiltration. So roof, in case of a roof, and attic or crawl space, they all gonna add up this natural infiltration. And let us talk about what is infiltration. Okay, after making a little bit of a sense of infiltration and ventilation and how they are working, why they are important, and let's see what is infiltration. Infiltration is described as the air that enters a building through the leaks, okay, and this is because of the construction quality. It might be wind pressure and also the temperature difference. So this is something like that happens, okay. And in houses, like the cooking odors, paint, and the cleaning smells are taken care of by opening the doors and the windows, which we mainly do this, and this is providing the natural infiltration. And why is quantification of a building infiltration is difficult? Again, it is difficult just because of these reasons, as I told you. It is really hard because many variables is involved in this one. So estimates are really hard for the infiltration. And lower infiltration rates in insulated and well-sealed buildings with less or without any operable windows. So this is definitely the way. And insulated and well-sealed buildings with less or without an operable windows require less fresh air change rates per hour. So fresh air intake. Why should fresh air intake or the air change? It's the same meaning. Requirement vary for winter and the summer times. And this is important, really important, because most of the calculations we are gonna be doing is gonna require this and the what authorities are suggesting. So during winter and the summertime, the fresh air intake is different, and winter air changes are about 50% larger than summer. Okay, this is really important. Winter air changes are about like 50% larger than summer. Why? Because of wind and the air temperature difference. So in the previous classes we've seen that the temperature, the temperature in the air actually it moves from warmer place to the colder place or a cooler place, and this happens through 4 different ways. And the main thing that we in the just one class before than this one that we covered, it is the conductance, okay, resistivity of the wall and members and parts of it, and also the conductance through the resistance values. So winter time, the temperature difference in and out is going to be high, and also there will be wind. That's why the winter air intake is 50% larger than the summer one. What does 1 air change per hour for a building mean? This is the basis of all our calculations. So 1 air change per hour means all the air in a building is replaced by outdoor fresh air in every hour. This is what it means. Okay, so again, what does 1 air change per hour for a building means? In 1 hour, all the air inside the house will be replaced with a fresh air. This is what it means. And most of the time, if you guys go to Home Depot or the Lowe's and look at the fans and see the fan ratings, and the fan ratings and heating cooling formulas are always based on the CFM values. So air change rate must be converted to the CFM always, so that we can do our calculations. We ensure that our calculations are gonna be okay. So how are we doing these calculations? And let's say that we have a room, the volume of a room, like the dimensions of a room, 9 feet by 12 feet by 8 feet. Okay, so this is the dimensions of the 3 dimensions X, Y, and Z coordinate system. It means that width, length, and height of the room. Okay, 9 feet, 12 feet, and 8 feet. And let's assume that 1.5 air change per hour is expected. And in this case, we can find the fresh outdoor air CFM for this room by multiplying the volume of the room. What is the volume of the room? 9 times 12 times 8. Okay, volume of the room times air changes per hour. It was 1.5. It is given to you. Even if it is not given, winter time it's 1.5 in general according to authorities, and summer time it is 1. Why winter time it is 1.5, sorry, and summertime it is 1? We just said it in the previous bullet. Because winter there's a wind and there's a huge temperature difference in and out. That's why it is 50% more than summer. So summer 1 is okay. If nothing is given to you, you have to take the summer as 1, and the winter 50% more of 1, which is 1.5. And you gotta divide everything to 60, because 60 minutes per hour. Okay, this is gonna give you the CFM. So again, volume times air changes per hour divided by 60 minutes. Okay, so this is gonna be the CFM value. For this example that I just told you, like a room with the measurements like 9 by 12 by 8, and with an air change of 1.5 per hour. So what's gonna be the value? 9 times 12 times 8, this is gonna be the value, times 1.5, which is the air change per hour, divided by 60. Why we are dividing it to 60? Because 60 minutes per hour. So the value is gonna be, result is gonna be 21.6. This is the CFM value. So if I give you the dimensions of a room, and if I give you the air change per hour for that room, and if I ask you what is the CFM value, which is find the fresh outdoor air CFM for this room, 9 by 12 by 8 room. So this is the calculation that you guys need to perform so that you can find what is gonna be the fresh outdoor air CFM is required for the room. Okay, again, volume of the room times air changes per hour divided by 60, which is the minutes in an hour. Okay, so the final result is 21.6 CFM, 21.6 CFM. Okay, let's move. And let's go and talk a little bit about the ventilation. So what is ventilation? And as we said in the previous slides, ventilation is required to replace the old air with the fresh air in a building, and ventilation is a requirement for well sealed buildings, constructions such as commercial buildings with or without any operable windows. So when we are saying the HVAC systems or HVAC systems, H for heating, V is for ventilation. So ventilation is required, and HVAC systems is providing that ventilation, and we just gotta know how much of a ventilation is required for those places, and we can size our HVAC systems accordingly. Okay, so ventilation refers to air brought into a building by fans or any other designed apertures, so as in HVAC systems. And here, fresh air brought in with fans. Why we need that? Because of the health reasons. We do not want the sick building lawsuits. We want to ensure that the odor-free air, fresh air, is available inside the living spaces. And in large buildings with a few operable buildings windows, in general there are not even any operable windows, so ventilation is really necessary to make sure that the healthy and odor-free conditions. So we really have to be careful on that one. And what two major conditions determine the quantity of ventilation air brought into a building? And as we said, number of occupants are important, and the activities that they are performing. Okay, so we said that minimum 15 CFM per person is required. So if we have one person inside it, it is just 15 CFM minimum. And if we have 10 people inside this place, we need at least 150 CFM. And their activities is important also. So if it's a theater with 500 people inside it, or if it's a gym with 500 people inside it, the requirement is not going to be the same. Because in a gym, people just burn calories, and calories or the fat, what is that? It is just actually carbon dioxide that you guys are giving out with your sweat. So it means that it is gonna contribute more to the air. So you guys are gonna produce more carbon dioxide, which needs more ventilation in those places. Okay, so if you go to big gym places, you will see that it is already ventilated, but also there are like big huge fans. So those fans are helping the air just circulate better. And maximum number of people expected to occupy a building should be used as a multiplier for ventilation quantity. This is exactly as I just said. Like, let's say that maximum number of people can use a gym. Let's say that it's 500 people, so 500 times, it's gonna be more than 15 this time because of the activities involved also. So it's gonna give us the maximum or the ventilation quality or quantity. Okay, so how much ventilation needs to be provided. And we set the people factor, okay, the occupants. Here you can see what it means. How do the people who occupy building spaces impact heat loss or heat gains? As a body, we just produce heat, okay? Any human being, any living animal, living organisms like human beings, animals, or even the trees and vegetables, they are some kind of sort of producing heat, okay? So anyone occupies a building space, they impact the heat loss and the heat gain. And since this is the case, we have to know the number of the people occupying that space first. The second thing is the activities the people are doing to find the people factor. So if you're just sitting at rest, such as in a school or in a theater, so you will not be producing so much of an moisture, which means that you're not gonna be sweating a lot, and you're not gonna your heart rate is gonna be anywhere between 60 to 70, 80 for a healthy people. So that's why you're not gonna produce so much of a heat. So look at the table here, heat gain from occupants table. And if you are seated at rest, the total heat is gonna be 330. Okay, this is the case of an theater or grad school classrooms and stuff. If you're in a restaurant, you're eating and just doing some sedentary work, okay, this is gonna jump to 500. So 250 out of this 500 will be coming from the sensible heat, and other 250 is gonna be coming from the latent heat. Okay, let's look at the very last row of this table. It says that bowling, you are doing a heavy work. Okay, your body is working, you are sweating, your breath is just going, it's increasing. Maybe it's around 100, 110 right now. So you are producing more heat. So you are contributing so much heat gain for the environment. So from seated at rest condition, 330, all the way now, you are bowling with a heavy work. It is 1450 total heat you are producing as a body. So we really have to be careful with this one. Okay, so in our calculations, activities are important. That's why we call it as the people or the occupant factor. And I have a question here, or an example actually. And in this example, what I told you with the numbers and stuff, let's just do it is the one more time to make sure, to ensure that we did understand how to calculate excuse me how to calculate infiltration and ventilation. And the question tells us that estimate the infiltration and ventilation air quantities for a 10,000 square feet of a school classroom building built in 1954. So the date here, the year here is telling us that there was not a good insulation at that time, or the insulation it's done is not really good in our time right now. And that's why we are gonna just think about like the poor insulation conditions. And the conditioned space is 12 feet high. So it's giving us the third dimension. It gives us the square feet of it. Area times the height is going to give us the volume, which we needed. And the total population is 320 students and teachers. So it's giving us the number of students as well. Number of occupants actually, not only the students, but students and the teachers. The next slide is going to be giving us the solution of it. But very first thing that we gotta assume here, okay, we have to assume that 1.5 air changes per hour in winter time, and 1.0, which is just 1 air change per hour during the summertime. Okay, this is like the authorities' recommendation. So in this case, let's calculate the infiltration CFM. And these are our assumptions. We are estimating 1.5. If it is not given to you, these are the numbers, guys. It's never gonna change, okay? If it is not given to you, something else. For infiltration, winter time is 50% more than the summertime, and it is 1.5. And the summertime, it is just 1 air change per hour. Since this is the case, what was our equation? Volume times air change per hour divided by 60. So the answer is gonna be in CFM. Okay, so what's the volume here? Volume is area, square feet of an area of the building, times the height. So area includes two dimensions, length and the width. And when we multiply it with the height, we are gonna getting the volume. So 12 times 10,000, which is gonna be our volume, and times 1.5. This is the assumption for the air change per hour. divided by 60. Why we are dividing it into 60? Again, 1.5 air changes per hour. But our infiltration is asked for CFM. What was the CFM? Cubic feet per minute. So the hour needs to be converted to the minute. So if we divide this value to the 60, which is 60 minutes in an hour, so hour is going to cancel out, which 1.5 air change per hour, and also 60 minutes per hour, they are going to cancel each other out, and the only thing is going to be left is going to be the minutes. Okay, so volume is in cubic feet because each of them are feet. Okay, like each unit for the volume, it is in a feet, and width is in feet, length is in feet, height is in feet. 3 feet, if you multiply it, it's gonna be cubic feet. That's why cubic feet per minute we are getting it. Okay, so during winter time it's 3000. During the summertime you're just gonna multiply. The only thing that you're gonna change actually here, volume times the air change per hour. It was 1.5 for the winter time. It's gonna be 1 in this case for the summertime. And when you do all the calculations, you're gonna see that it is 2000 CFM in summertime. So this is the infiltration CFM. So now we are gonna calculate the ventilation, and we know that ventilation is needed. Ventilation is needed for places, especially well-sealed, tight buildings. And we said that we gotta assume minimum 15 CFM. If something else given to us for like the school case, we have to use those numbers. And your book has a table, and it provides some different numbers for different building spaces. So you can use the table, but minimum 15 CFM per person, you guys have to select it. And we said that there were 320 occupants, which is students and the teachers altogether. What we are gonna do, CFM per person times the number of students, 15 times 320, and this is 4,800 ventilation CFM required for all year. So during the summertime, there will be 2000 CFM from infiltration and 4800 CFM for ventilation. So total is 6800 CFMs during the summertime. And winter time, 4800 plus 3000 is gonna be 7800 CFM during the winter time. Okay, and there are a few things actually. Most of the time this is very basic calculation that we are doing, but you guys gotta be careful about the ventilation fans. They pressurize the building, and finally they overcome the anticipated infiltration actually. So since they are pressurizing it, so they really overcome the anticipated infiltration, whatever we are thinking about. But still, this type of calculation should be fine. So this is what suggests us, okay? And the way that I just mentioned to you, during the summertime it is 68 CFM, during the winter time it is 78 CFM. So this is gonna be extremely conservative. Okay, so if you're using this design, so more conservative designers add infiltration and ventilation CFM to allow for exhaust fans and the door openings. And again, as I said, it's gonna be really conservative design, and it is not gonna help us with the good size. We will be just spending so much money actually in the ventilation system. That's why the most important thing here to take the largest of these values and use it as an infiltration and a ventilation value. Okay, what it means, during the winter time infiltration CFM is 3000 and ventilation is 48 CFM. So I have to use ventilation CFM, which is 4800, which is larger than 3000. So I am just going to use a larger number. I am not adding them. if I add them, it's gonna be conservative and it's gonna cause us to get a larger equipment size and pay so much money on it. That's why I'm using the higher of ventilation or infiltration in my calculation. Okay, so in the previously or the conservative designers are still adding them up. However, please do not forget that ventilation fans pressurize the building, so overcome the anticipated infiltration. That's why most of the time your calculations of infiltration and ventilation, you will see that ventilation is going to be larger than the infiltration. So always you guys are going to be using the ventilation in that case, since this is the ventilation case. Okay, regardless, we are calculating infiltration and the ventilation, and we are using the larger one for winter and the summer cases. Okay, so let's keep going. We have really so many slides to cover in this class. And the other thing is electricity lighting factor. So how does using electricity as a result of powering light fixtures impact heat? It says it impacts a lot actually, because we know that the bulbs and any type of light, fluorescent lights or even the LED lights, very little, almost nothing, but still they contribute to the heat of the environment. So they are like the heat gains for us. So what type of fixtures create more heat gains, fluorescent or incandescent lights? This is a little bit hard for me to say, but it's just the light bulbs. Okay, so fluorescent, all the bulbs which provides more heat. In the next one, you see that the bulbs heat gain is 3.41 BTUs per watt, and fluorescent lights is 4.25 BTUs per watt. So in this case, which one is providing more heat per watt? Is the fluorescent lights. So the fluorescent lights have more heat gain because of the larger quantities of given off by the blast in a fluorescent light. Okay, so larger quantities of heat given off by the blast in a fluorescent light. So again, we are not factoring the LEDs. Okay, so we are just looking at the difference between fluorescent and the bulb light here, light bulb here. So as you can see from the numbers per watt, bulbs are producing 341 and fluorescent light is producing 425 BTUs. Here in this slide, we are just comparing them. So for the bulb, you can get equivalent for the fluorescent light. So 25 watt of a fluorescent bulb gives the same lumen for the 5 watt fluorescent light can do it. Okay, so even though per watt fluorescent lights provides more heat, however, since the lumens, the brightness wise, fluorescent lights provide more per watt. So instead of 40 watt bulb, you can use 10 watt fluorescent light. They are gonna provide the same amount of the lumens, same amount of the shyness or the lights inside the space. So using a fluorescent light 10 times 425, it is gonna be providing 42.5 BTUs. But to get the same amount of the light, if you're using an incandescent bulb, so this time 40 watts times 3.41, it's gonna be 136.4 BTUs. Okay, so even though per watt the fluorescent light has more BTUs, when it comes to the brightness, when it comes to the lumens, fluorescent lights are causing less heat gain. Okay, so this is another important thing that you guys really need to do, and we are gonna integrate this into our calculations. Let's go look at a little bit electricity and the fuel appliances that we use in our houses, and they contribute to the heat gain in the calculations. So if you are using like a burner, toaster, hair dryer, any type of those equipments are gonna provide some heat gain. Okay, so if they are running with electric, or if they are running with gas, if they are under hood or without hood, all these numbers are gonna change. And roughly, let's look at the deep fat fryer. Okay, so it is like the second is this one. Okay, I'm looking at the deep fat fryer for 15 pound of fat that is used. And if it is electric heated, okay, so it is providing like a 2800 sensible heat and 6600 of a sensible latent heat. Together it's 9400, okay, without hood. If you have a hood, all is gonna be the sensible, or the latent heat will be sucked with by hood, so there won't be any latent heat. So this value is gonna be around like 3000. And if it's a gas heated without hood, sensible is gonna be 7500, latent is gonna be another 7500, so the total is gonna be 15,000. Okay, if you have a hood, again it's gonna be the same thing, like 3000 as in electric case. Okay, so according to the appliance and according to the type of appliance, actually we can use this table to integrate it into our heat gain and heat loss tables. Let's keep moving. And efficiency and the outdoor air. I know this slide, or this lecture is gonna be a little bit longer one, and you might wanna just stop it at some point, just observe what you are learning, and then watch the second part of it. I could make like 2 different classes for this one, but I felt like it's gonna be better to combine or just finish everything that is gonna be included in the heat gain and loss calculations in one presentation and one lecture. So whenever you need it, instead of going to different places, just under one video you can reach hopefully everything that you need. Let's see the efficiency and the outdoor air. And efficient buildings conserve energy. How? This way, by minimizing the outdoor air quantities and using heat exchangers to temper outdoor air, and using an economizer instead of refrigeration equipment. Okay, so for heat-rich buildings in the winter, include air intakes and the dampers that permit the use of outdoor air instead of refrigeration for building cooling when outdoor temperature conditions are right. So there are some terminology here, and the first thing is our goal is to conserve energy in efficient buildings. So to conserve an energy, we have to minimize the outdoor air quantities so that all the air, conditioned air, is gonna be staying inside. And if you minimize the outdoor air quantities, that's good to conserve energy. So minimum outdoor air means just a minimum heating and cooling costs. Tight buildings with carefully controlled ventilation rates can save heating and cooling energy tremendously. Really it does. So that's good to minimize or to conserve the energy and minimize the outdoor air quantities. And appropriate design strategies include quality construction and provision for reduced outdoor air on nights or weekends, or whenever building occupancy drops. So if it is really controlled, well done construction, even there are no occupants inside it, it's still gonna reduce for the outdoor air on nights or weekends, okay, when there are less occupants inside. And using heat exchangers to temper outdoor air, it says. So this is when you can think this way: when outdoor air is brought into a building, it displaces the conditioned air. So outdoor air is coming into the building and displacing the conditioned air inside. So efficient buildings include heat exchangers to temper outdoor air. When outdoor air is brought into a building, it displaces the conditioned air. Okay, actually I'm repeating myself here. So efficient buildings include heat exchangers to transfer heat between exhaust air and incoming outdoor air. This is the most important thing. So efficient buildings, they have the heat exchangers. So those heat exchangers transfers the heat between exhaust air. That exhaust air means the air that is taking out of the building, and taking that heat, okay, and giving that heat through the heat exchangers to an incoming outdoor air. Okay, so the job of the heat exchangers to transfer the heat from exhaust air to the new outdoor air. Okay, so this is the job of the heat exchangers, and they're used really in the efficient buildings. Let's say that there are like LEED certified buildings, green buildings. They all have the heat exchangers, and heat exchangers are really saving a lot of money for the heating purposes. And the other one is saying that the economizer, and economizer, you guys think this way, and actually next bullet is explaining that one. So many large buildings are heat rich. So it means that the buildings are so high, so well sealed, well tight. There are so many occupants inside it, so many appliances, so many lights inside it, such as in a skyscraper. Okay, so high-rise buildings. So there are so many things that contribute to the heat. So they are called as heat-rich buildings. Okay, so from lights, from people, equipment, and anything. So in a moderate winter days, they don't almost need any heat provided to those ones. So such buildings operate air conditioning equipment in winter to remove the internal heat. Okay, so that's why economizers just describes like the air intakes and the dampers, which permit the use of outdoor air instead of the refrigeration for building cooling when the outdoor temperature conditions are right. Okay, so even better is an enthalpy controlled economizers, which is available in nowadays. What enthalpy controlled economizers do, they evaluate both outdoor temperature and the humidity. Don't forget, it is enthalpy controlled. Enthalpy is latent and the sensible heat. That's why they assess both the outdoor temperature and the humidity, then mixes appropriate quantities of air outdoor and the indoor air to achieve a comfortable conditions without doing any refrigeration. So heat exchangers and the economizers are good, and they really needed for to provide like a sustainable future. Okay, so these are like the two terms that really needed for us to know. And let's go to next slide, and it says that why calculate the loads. Okay, the main goal of calculating the loads, heating and cooling loads actually, to select the heating and cooling equipment, and also estimate the annual heating costs. Most of the time the anything like the Gulf Power or DT Energy, wherever in the different part of the states or the world, there are companies that they provide you the power, electricity, or the propane or the natural gas, doesn't matter. So those companies are calculating your annual cost, and most of the time they are gonna offer you some different options. So this is one of those reasons. So estimating the annual heating cost. Also, you would like to know how much you're gonna be paying for your gas or the electric bill. Okay, so these are the two main reasons: selecting the heating equipment, the right size, and also estimating the annual heating costs. And how are we doing this type of calculations? There are two ways of doing these calculations, and in one of them we are doing it like manually, conventional way. Just we have the tables which we are gonna do in this class. There are tables, we are using those tables and just getting our heating and cooling loads according to the appliances, according to the number of people, according to the infiltration and ventilation requirements. And the second way is just computer-aided load calculations. And most of the things nowadays, you know, there are computers, and you can use those softwares to do the heating and cooling load calculations. And I mean, that's really easy, straightforward softwares, just a series of commands that request the data from the operator. As an operator, you are just giving the data and manipulating the data actually to determine the heating and the cooling loads. That's what the computer-aided load calculations are does. And really similar to the conventional method, which is the manual method. However, instead of human being, just a computer perform all those calculations. And really they are doing the same thing actually, but computer aided load calculations using a software that does the job for you. In our case, we will be using the conventional, which is the manual load calculations, where you guys are gonna perform all the calculations and gonna come up with the right size of the equipment. You're gonna decide on the size of the equipment. And why we are doing this, even though there are computer aided load calculations, because we would like to learn. I want you guys to learn. Some of you guys maybe end up working with HVAC companies, which previous year students who are graduated already, and so some of them are working for the HVAC companies, and they came and asked for these presentations. So they wanted to integrate. They wanted to actually go over the things and integrate more of them into their jobs. So this is really helpful. So what is this tabular form? Tabulated, it says. Let's see the table. Okay, this is one of those tables. It is the one that you have in your class book, textbook, and I'll be using this one. And in this one, there are different tables. There are so many different tables. H-Rays has a way different tables. It is provided, and your book is giving this one. This is very easy to use, and we will be mostly going over this one. And first of all, we have the project name and the location and a square foot of the area. So that by knowing the square foot of an area and also the height in general, we will have the blueprints of the house, so we can easily calculate all these things. And fill this table out. Filling this is easy and it is not easy at the same time. And as you can see, there are project conditions. Project conditions is used to calculate the CFM values for the infiltration and the ventilation. And then there are glass lighting, people, ceiling, roof, U values for the walls and floors. All those U values are gonna come from, what was the U value? It was a conductance value. It is nothing but 1 over R, which is resistance, resistivity for the material. So we are gonna get all those, we are gonna perform all those calculations, and after that we are gonna do the load calculations. And in the design conditions, we know the indoor and the outdoor winter temperatures. Indoor temperature during winter time, it's like 70 degrees Fahrenheit. This is what is people preferences, and 65 is like the, I believe it is 65 for the authorities recommendation and 70 for the people's preference. So we can always check. And during the summertime, it's 75 for the authorities recommendation and 70 for people preferences. That's how I remember, if I'm not mistaken. It's on the previous class, and we are definitely gonna go check those slides. And for the design conditions, it's gonna be the indoor dry bulb temperature, and outdoor is whatever the outdoor. It is like the quantity, peak heat loss or heat gain calculations. We are doing it, and we have the heat maps. So from heat maps we can calculate the outdoor temperatures, like the coolest temperature for the elevation that that location has. And for the winter case is this one. For the summer case there are some other numbers such as the relative humidity. Summertime it's so humid, we all know that, so we have to keep the humidity at around like 50%. So 50% again the authority's recommendation. So indoor relative humidity 50% is gonna be nice. So by using all these values and the psychrometric charts, we are gonna calculate our grain difference, and we are gonna use all these ones in our calculations. So I will prepare another video most probably next week class time. It will be the calculations, and you guys are gonna have your quiz and the assignment related with that calculations and all these chapters, of course, the last two chapters that we are covering. And so far just it is good that you guys know that there are tables, and I'm gonna solve an example how to fill those tables, how to get those numbers, how to do the winter heat loss and summer heat gain calculations, at the end how to size the equipment. Okay, so there's another type of form which is filled out, and this is again, as I said, there are very different type of forms, and ultimately they yield to the same or very similar results. And the variables, design temperatures, and the building data. What are the variables used to calculate heating and the cooling loads? And they are all in the table that we are again going to cover them, and I will cover them when I am filling out that table. So the variables for calculating heating and cooling include the design temperature differences, area of a building, and the infiltration and ventilation loss or the gains, number of people, so number of lights and appliances. These are all the variables used to calculate heating and the cooling loads. We just covered all this stuff. And what is design temperature, indoor and outdoor? So the design temperature is the temperature of the air at a predetermined set of conditions, and indoor design temperature is like the at the inside of the buildings, which is 70 degree. I said 70 degrees for winter and 75 degrees for summer. Okay, yes, 70 degrees for winter and 75 degrees for summer case, indoor design temperatures. And outdoor design temperatures will be taken as the coldest temperature during 97.5% of the winter and the warmest expected temperature for 95% of the summertime. So we are not getting just one value, we are getting the 97.5 for the winter case and 95% of the summer temperatures. So we are saying that this is the temperature, outdoor temperature for us. And indoor temperatures, again, they are not changing. For the winter time, we are taking it 70 degrees, and for the summertime, we are taking it as 75 degrees. This is the authorities' recommended values. And another thing is the building data. What is building data, and how are plans and specifications used in determining load calculations? Building data is the name of like each room, running feet of exposed walls, and the dimensions like the ceiling height or exposure of the each room to the sun, like the orientation, like the compass directions and everything. Okay, this is like the building data. And for load calculations during the planning and the construction phase, all the plans and specifications, blueprint readings, they are going to provide us the building data needed. Okay, so we can get all our building data from the plans and the specifications for the if they are available, of course. And sometimes they will not be available. There might be some just sketches in the city halls or something. Even sometimes you cannot reach those ones, you can easily make some sketches and some basic measurements. Nowadays the technology is really good. There are like the handheld devices that measures the direction, compass direction, orientation, and the length, height, any type of dimensions. So by using those ones, you can make basic sketches and you can use it as the building data. And sample design temperatures for some state and cities are provided in this table. So there are different tables like that. This is from your book and just giving according to the latitude values. Some winter dry bulb temperature and summer dry and wet bulb temperature. Also the humidity wise provided here. And building data sketches, this is something like this. Okay, so in the worst case scenario, as I said, if you don't have anything, we can just create one. It's really not hard. We're just gonna go a few people, 2 people is enough, 3 is better, to measure the sizes of the building and make some basic sketches, show the dimensions on that one so that we can calculate the volume. We can based on that calculations we can do all other our calculations. And this slide is like a repetitive slide that I had it like 2 classes ago. So sensible heat, latent heat, and the enthalpy or the total heat. So this is the type of heat that HVAC systems deal or must deal with. So sensible heat, if you need to calculate the sensible heat, this is the equation here. We know the CFM, okay, cubic feet per minute. So we are multiplying it with the temperature difference and with a constant 1.08. And if we are gonna do this for the heat gain of the latent heat, it's gonna be CFM times 0.68 is the multiplier, and this time instead of temperature difference gonna be the grain difference. Why the latent heat related with the grain difference? Because we are talking about the water vapor in the air. That's why we have to get the grain difference. And if we are talking about the enthalpy, just calculate sensible heat and the latent heat together and add them up. This is going to give us the enthalpy. Or by easily CFM times 4.5 as a multiplier, and ED is the equivalent temperature difference. So by using these equations, we can calculate any type of the heat or the enthalpy that needed. And these are going to be needed also for us. And how it is going to be needed here. How does cold air, winter air leak into a building? And we know that it leaks into a building through the doors, windows, and other like small openings found on the skin of a typical building. And well-sealed buildings maintain air quality through well-sealed buildings actually constantly exhaust indoor air and replace it with the outdoor air to maintain the air quality. So it is just the exhaust system, just take the indoor air and replace it with the outdoor air. And heating equipment must be sized to heat this admitted outdoor air. Heat losses caused by infiltration and ventilation air are calculated. How? By using this. Okay, CFMs are calculated through the infiltration or ventilation. We said that whichever is the larger one, infiltration or ventilation, whichever is the larger one in terms of CFM, we are going to be using that one in this equation. And the conducted heat losses are calculated by conducted heat losses happens on the skin of the building, and it's calculated by using this equation. U is being our conductance, which is 1 over total R of the skin of the building. If it is a wall, just the different layers of the wall material. So we are getting all the R values, total R value we are calculating. 1 over R value is the conductance value, which is U. times the area times the temperature difference in and out. Okay, so this is gonna give us the BTUs, British thermal units per hour. And there was an example in the previous class, and it was just making these calculations for it, and for each material it was calculating the temperature drop from indoor to the outdoor during the winter condition. And let's say that we have an 12,000 square foot of an roof, and it is U value is 0.15, which is 0.15 actually, which is better for you to just follow it up. So U value is 0.15 and the area is 12,000 square foot. This is our roof. And if indoor temperature is 70 degrees and the outside temperature is 10 degrees, what's gonna be the heat loss here in terms of BTUs? We are gonna use this conducted heat losses equation here. So U value is 0.15, area is 12,000 square feet, which is the roof, and the temperature difference is 70, which is the indoor, 10 is outdoor, 70 minus 10, which is 60. So when you multiply everything, you will end up getting like 108,000 BTUH, okay, British thermal units per hour. And if I need to give you an example with the use of infiltration and ventilation example, let's think of a building which has an infiltration rate of 4,000 and a ventilation rate of 6,000 CFM, and let's calculate the BTU heat losses when indoor temperature is 70 and the outdoor temperature is, let's take it 0 now. Okay, so indoor is 70, outdoor temperature is 0. So the temperature difference here, it is 70 minus 0, which is 70. 1.08 is 1.08, it is not changing. And infiltration rate was 4,000 and ventilation rate was 6,000. So I gotta use the larger one of them. And 6,000 is larger than 4,000, so I'm gonna use the 6,000 here as the CFM value. So 6,000 times 1.08 times 70. And this is gonna be so 1.08 times 7. It is 453,600 BTUH. Okay, 453,600 BTUH. And how do we derive a building's total heat loss? Okay, so the total heat loss is gonna be a combination of all these. Okay, so we know that the total heat loss is gonna be a combination of all these. Estimated building heat losses, and a building's largest or peak heat loss is calculated as to determine the size of heating equipment and also to estimate the annual operating costs or savings or for energy conserving alternatives. So first we are gonna size the heating equipment, and the upcoming classes we are gonna see how to calculate the operating costs, and also we are gonna see if like using a gas equipment or an electrical equipment is gonna be logical for us. We are gonna see those ones also. And heat leaves a building by only 2 routes. So what are those 2 routes? It is the building skin conducts heat to colder outdoor surroundings, and cold outdoor air replaces heated indoor air. And again, the rate of heat loss is determined by a U value of the skin, and the equation is again this one: U times area times TD, temperature difference. This equation is really important for us, so we will be using it a lot. And what was BTU? BTU is British thermal units. It is the amount of the heat required to increase the temperature of 1 pound of water for 1 Fahrenheit degrees. Okay, so this is the BTU. So in order to, what is BTUH then? To increase the temperature of 1 pound of water 1 Fahrenheit degrees in 1 hour. So this is the BTUH. It's the definition of it. And this is really important terms. And in the beginning of each chapter in your book, there are glossary, there's terminology. You guys can just use those ones. They are really good. They are really helpful. I mean, I let you use those ones because most of the time I even forgot sometimes the exact definitions. So I need to go and take a look at it. In general, I don't forget the definitions, but I might forget the equation wise, so it's always good to create a type of sheet and include all the equations and just see where you guys need to use those ones. They are going to be really helpful during the exams and previous exams and the upcoming quizzes. And let's go to our next slide. Estimating building heat gains. So how building is gaining a heat? 3 additional factors while calculating the heat gain. So sun, internal heat loss, and the latent heat. And through the sun we gain some solar heat through the glasses. So in order to calculate that, this is the equation that we are going to use. SF times A times SC. Okay, so area is A, SC is the solar shading coefficient, solar factor is SF, and the SC is the shading coefficient. So there are different type of windows, and those different type of windows provide different U values, and since they have different U values, the shading coefficient is different for them also. Each of them, they have a different U value, and of course in return the SC and SF values. If you go to Home Depot or the Lowe's, if you look at some windows, and you will see there are stickers on them, and it rates all these SC and SF values on them. And there will be another heat gain. This is gonna be the conducted heat gain through the glass. What is the conducted heat gain? Again, it is nothing but U times A times the temperature difference. And if you see this equation, and if the question is asking you what type of heat gain or loss can calculate by using this equation, it has to be conducted. Okay, don't forget that one. And heat gain through opaque roofs on the walls, and this is gonna be U times A, same way. It is again like the conducted heat, but instead of the TD, this time the ET, the equivalent temperature difference. So there are tables in your book, it is talking about the equivalent temperature differences. And there are 4 special cases of heat loss, and I know guys we are almost done. There are 4 special cases of the heat losses. So since they are special cases, I really tend to ask questions about them, and anywhere you guys can find the questions related with these ones, because they are just special cases. So these special cases, they do not fit the preceding heat loss formulas that we just covered. Okay, one of them, the ducts or the piping outside the conditioned space. In a little bit I'm going to show a picture of it, what it means. So if your HVAC system is outside and the ducts or the piping that goes in a conditioned space comes from the equipment, and it's gonna there's no way that you can calculate it. It's a lot of work, so we just take it as is. So there are basement walls and the floors and insulated but unheated spaces adjacent to the conditioned spaces. So such as garage. Okay, so it is insulated but unheated space adjacent to the conditioned space. If you're in an attached garage, so it is insulated sometimes, most of the time, but it is unheated. Some people just want it to be heated. It's another type of an fantasy to wait to spend more money, but most of the time they are insulated but unheated. That's why this is the other condition. And there's another case, that fourth case is exposed slab edge losses. So in the foundation, slab on grade type of a foundation, so the foundation is larger than the house seating itself, so exposed edges of that slab causes the heat losses, and that is the fourth case. The fourth case is shown a little bit different than the other three cases, because we can just make the assumptions for the fourth case how we are doing it. And the exposed slab edges will fit with an allowance, okay, to the equation U times A times TD, okay, conductance times area times the temperature difference equation. It will fit it to that equation. However, allow extra 1 feet square of an area for each linear foot of slab edge. Okay, so when I am doing these calculations, you guys are gonna see what it means exactly, but just make a note somewhere for the exposed slab edge losses. We can still use the U times A times TD equation, which is the heat conducted heat equation, but allowing an extra 1 square feet of area for each linear foot of slab edge. Also for the third case, insulated but unheated spaces adjacent to the condition space, we are kind of using U times A times CD equation, but this time we are reducing the temperature difference by 50% to account for the reduced heat flow, and only half of the area involved will be included in the equation. So this is another thing you guys should make a note of it, and when I am filling out the tables and do the calculations, that time I'm going to mention about these ones, and you guys are going to apply the same thing in your homework assignments. And this is the ducts and piping outside the conditioned space. This is the picture that I'm talking, and this is the case. Okay, and if they are just outside, heating and cooling system, HVAC system, so some ducts in the pipe just outside the conditioned space, we cannot do any calculations for those ones. We can always assume something, but we can't do exact calculations, and we are not doing it actually. So, but these are the special cases. It's good to know. You definitely can get some questions from that. And internal loss and the latent heat gains. This is like the really last two slides that I'm gonna cover. This is the internal loads and the latent heat gains. And internal loads include heat gains from lights, people, motors, kitchens, and other equipment. Okay, so not only like the ventilation and infiltration or just conductance heat, but also we can gain heat from lights, people, motors, and some other equipment. For the people heat gain, number of people times BTUH for the per person, and this BTUH per person is varies with the activities. Okay, so if you are in a gym, it is different. If you are in a theater or a schoolroom or just in a building, it is different. And even in a space right now that I am in, since I have been running some electricity, some computer, and I am talking and just producing some heat, my HVAC system started to run in an AC site. So you might hear that one. So it is just because of the lighting inside the place, the heat provided by the lighting, and also the heat that my body provides into the system. Okay, and there's a motor heat gain if there's any motor inside the conditioned space. So the BTUH calculation will be horsepower times 2500 per horsepower hour. Okay, so this is the calculation. So if it is 10 horsepower equipment, it's gonna be like 25,000 BTUH. Okay, And if there's a light heat gain, and you know the light heat gain, we covered it, total watts times the 3.4. This is for the bulbs, okay, per watt hour. And latent heat is gonna be the heat that exists in the water vapor, which is carried by the air. We just call it like the humidity. Okay, so the calculation of it is CFM times 0.68 times the grain difference. This is a latent heat gain, and we covered it a few times. Let's go to I believe the last slide of this lecture, internal loss and the heat gains. So one more time, and the last time, I'm talking about heat gain calculations are used for selecting the air conditioning equipment and estimating the annual cooling costs, and quantities changes for heat gain are emphasized as the outdoor air. And we know that we are going to use a larger value of the infiltration or ventilation, and we know that winter infiltration is going to be 50% more than the summer infiltration, and in some places you can see it like the 67%. It's another value. They are saying that instead of 50% they are making like 2/3 of it. It makes like 66. They call it 66.6. They call it as 67%. So please just stick to the 50% for this class, but know that those values are sometimes changing. And then we are gonna calculate the glosses, and we are gonna calculate the conducted heat gain through the glosses. So we are gonna use the total glass area, and then we are gonna subdivide this total area into like proper compass orientations to calculate the solar heat gain. And if there are like the skylights, we are just gonna enter them as the horizontal glass. And for the lighting, we are gonna enter the total watts of the lighting that will be operated at peak heat gain time. This is important. We have to calculate them at peak heat gain time, because it is like the night time, okay, not during the daytime. Daytime we are not using any lighting equipment. Be careful with that one. And then the number of people, and we are gonna just enter the number of people that occupy the building at the peak heat gain time again. And the other one is ceiling, roof, and walls. Make sure to remember to deducting the window and skylight areas. And in general, it's really hard to find an exact U value. That's why we use an average U value, especially if the building has a variety of roof and a wall construction, which is the case. Okay, so these are the things that we really need to calculate. And after that, we are just gonna make like our calculations. And finally, actually, for any typical United States constructed buildings, the total heat gain should be around like 15 to 60 BTUs per square feet of an air conditioned floor area. Okay, this is important. So this is like the self check. It is also under the tables. It's given to you. And I will wrap up. I'll finish the class here with this slide, and please let me know if you guys have any questions.